Well, thank you very much. It's an honor to be here, and it's a wonderful institute. It's a great program, and I'm very impressed with the institute. So I was instructed to make this very non-technical. I actually prepared two talks, one slightly more technical, but I'm going to stick to my charge. So I'm afraid everyone's just going to be bored, but I will give you a treat at the end. Okay, so we'll begin. All right, so arguably in the domain of classical mathematics, we have the objects which are just the whole numbers, and we have our basic operations, plus and times, and we have the simple rules for addition and multiplication, and we have the principle of induction, that every set of counting numbers, if not empty, contains a least element. And arguably, all of classical mathematics evolves from this conception. That's it. Okay, now I'm simplifying things, but one can make a case for that. A lot of, it depends on what you mean by classical, I suppose. So it could be by definition. All right, so we want to now move beyond classical mathematics into the realm of the infinite. And so the mathematical story of infinity arguably begins very modestly with the empty set. That's quite simple. Well, I'm now in a philosophy department, and I guess one could say the empty set's quite complicated, but I won't talk about that. It's important as you age to go into new careers and so forth. Anyway, so we generalize the counting numbers into what are called the transfinite numbers. They're known as the ordinals. So the empty set is the smallest ordinal. That was 0. And then you have the set whose only member is the empty set. That's 1. And then the next one, and so forth. If alpha is an ordinal, it's just a set of all smaller ordinals. And if you want to get the next largest ordinal, you just take alpha union singleton alpha. So those are the transfinite numbers. Omega denotes the least infinite ordinal, and it's the set of all finite ordinals. Now, ordinals can be added. Subtraction is a bit dicey, but they're in some sense a nice generalization of the counting numbers. The important thing is that they stratify the universe of sets, and the universe of sets is where we look at infinity. So we need an operation, that's the power set operation. That's the exponential function in set theory. So again, the concept is a simple one. If x is a set, the power set of the set x is just a collection of all subsets of that set. Okay, so if x were a finite set with n elements, the power set of x would have 2 to the n elements, and that's why it's an exponential function. Using the power set function and the ordinals, we can form the cumulative hierarchy of sets. So we start again with that object, the empty set. At a successor step, we just take the power set of what we have, and at a limit stage, we take the union. And you can show by induction that if alpha is less than beta, V alpha is a subset of V beta. It's an increasing hierarchy. It's a consequence of the axioms that every set belongs to some V alpha. Well, so there it is. That's the universe of sets. Maybe it's not so complicated after all. And maybe we could just figure out what V0 is, then understand V1. You have to do the inductive step. If you understand V alpha, you go to V alpha plus 1 and so forth. All right, well, let's look at these V alphas. Well, V0 is the empty set. V1 has only one element, and that is the empty set. V2 has 2 elements, the empty set and the singleton set containing the empty set. These are just the ordinals 0, 1, and 2, by how I define the ordinals. V3 has 4 elements. It's not the ordinal 3, and it's not an ordinal. All right, so it's a little more complicated. V4 has 16 elements. Okay, don't panic. V5 has 65,536 elements. Now start panicking. V sub 1,000 has a lot of elements. Okay, so these, because it's an iterated exponential, powers of 2, the sizes of the VNs are getting big very quickly. V sub 1,000 is a very complicated object combinatorially. V omega is infinite, and it's a set of all hereditarily finite sets. So it's at V omega that you transition from the finite to the infinite, and the conception of V omega from the set theoretic point of view is mathematically identical to the conception of the integers with plus and times. They're just two aspects of the same thing. So in this sense, V is generalizing the structure which gave birth to most of mathematics, that structure. But now we're going to move beyond. Okay, so what are the axioms? The ZFC axioms, I'm not going to define them, are the current accepted family of axioms. You can think of them as specifying the laws of our conception of V. V is the universe of sets. And it's a consequence of the ZFC axioms that every set belongs to some V alpha. It's a consequence of the ZFC axioms that for every ordinal alpha, V alpha exists as a set. Okay, so it's the framework for doing the constructions that I was talking about. But somehow we want to go beyond that. So the axioms, the ZFC axioms, are naturally augmented by additional principles which assert the existence of very large infinite sets. These additional principles are called large cardinal axioms. And here I'm going to give you some samples. Proper class of measurable cardinals. Measurable cardinal is a conception, it's a large cardinal. To say you have a proper class just says for every alpha, there's a cardinal bigger than alpha with that property. Okay, then bigger than measurable are strong cardinals. My favorite, proper class of Woodin cardinals. Super strong, names aren't terribly imaginative. Then super compact, extendable, huge, omega huge, and these are just mileposts in the large cardinal hierarchy. Okay, so I'm just illustrating that there are a lot of these principles. All right, so let's look at some simple infinite sets. We want to start talking about infinite sets. Well, N is a pretty simple infinite set. Z, the set of all whole numbers, positive and negative with 0, that's a simple infinite set. The rationals, ratios of integers, the real numbers, and the points in the plane. These are natural, simple infinite sets that arose classically. So we'd now like to compare sizes of infinite sets. We want to understand this realm. So if you have two sets, x and y, they have the same cardinality if there's a matching of the elements of x with the elements of y. It's exactly how you measure or say that something has 3 elements. There's a matching with 3. Formally, we write x and y have the same cardinality if there's a bijection from x to y. So if we look at our simple infinite sets, it's pretty clear that the numbers 0, 1, 2, dot, 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 and the numbers 1, 2, 3, dot, dot, dot have the same cardinality. Just add 1, that's your bijection. More tedious is to verify those 3 simple infinite sets all have the same cardinality. Much less obvious is that the points on the line and the points in the plane, those 2 simple infinite sets have the same cardinality. Okay. So if you assume the ZFC axioms, then for every set x, there's an ordinal alpha such that the cardinality of x is the cardinality of alpha. So in that sense, the ordinals really do generalize the positive integers. The only subtlety is an ordinal can have the same size as a smaller ordinal. But for every ordinal, there's a least ordinal of that size. That's a cardinal. And those, in some sense, are another generalization of the counting numbers. I won't say much about that. Omega is a cardinal, omega plus 1 is not. Okay, so now we come to the continuum hypothesis. This is the first question you would ask if you were looking at the universe of sets, and it's one of the first questions that was asked. Well, first we need to compare the sizes of the infinity of the naturals and the infinity of the reals, and it's Cantor's famous theorem that these sets do not have the same cardinality, so there really are different sizes of infinity. Well, once you realize that, you want to now ask the question for the continuum hypothesis. Suppose you have an infinite set of real numbers. Must it either have cardinality of the naturals or cardinality of all the real numbers? In other words, in some sense, it's saying, is the infinity of the real numbers the smallest infinity bigger than the infinity of the naturals? That's Cantor's continuum hypothesis. Okay, now I'm going to do something very dangerous. I went to Wikipedia. Okay, so if what I'm about to say is historically incorrect, I blame Wikipedia. If it's correct, it's my scholarship. First, this is Cantor's continuum hypothesis. By the examples that I gave, the continuum hypothesis holds for those simple infinite sets, and in fact holds for many not so simple infinite sets. If you look at many natural infinite sets that have arisen, you don't see a counterexample to that formulation of the continuum hypothesis. Okay, now we get to the Wikipedia research. Well, no, this isn't Wikipedia. In 1900, at the Second International Mathematical Congress in Paris, Hilbert posed his famous list to guide the development of mathematics for the coming century. That was last century. The problem of the continuum hypothesis was the first problem on the list. And it was a relatively new problem at that stage. In 1904, at the Third International Mathematical Congress in Heidelberg, Cohen gave a lecture in which he claimed to solve CH. This is Wikipedia. All parallel sessions of the Congress were canceled so that everyone could attend Koenig's lecture. The announcement was a sensation and was widely reported by the press. The Grand Duke Frederick I of Prussia had Felix Klein explain the entire matter to him personally. The proof was wrong. Okay, so I don't know how Felix Klein dealt with that little issue, but all right. So many others tried to solve the problem, and they also failed. Hilbert thought he had a solution for 2 years. Wikipedia. The problem with the continuum hypothesis quickly became to be widely regarded as one of the most important problems in all of modern mathematics. Okay, in 1940, Gödel showed that it's consistent with the axioms of set theory, the ZFC axiom, that the continuum hypothesis be true, so one cannot refute the continuum hypothesis. In 1963, on July 4th, Cohen announced in a lecture at Berkeley that it's consistent with the axioms of set theory that the continuum hypothesis be false, so one cannot prove the continuum hypothesis. Now, for those of you who aren't from the US, the July 4th has no meaning to you, but this gives you some insight into Cohen. July 4th is Independence Day. So I don't think that was a random choice of date. All right, so what is Cohen's method? I'm not going to get technical. If M is a universe of set theory, so that's a structure, think of it algebraically, in which all the axioms hold, then within M there are blueprints for virtual universes which extend M. These blueprints can be constructed and analyzed from within M. If M is countable, so as an object, then every blueprint constructed within M can be realized as a genuine extension of M. So Cohen solved the extension problem. Gödel solved the submodel problem. Cohen solved the extension problem. Entirely analogous with fields in some sense. Cohen proved that every universe M contains a blueprint for an extension in which the continuum hypothesis is false. So that's how he got his theorem. Now, Cohen's method also shows that every universe contains a blueprint for an extension in which the continuum hypothesis is true, so you can recover Gödel's result as well. Levy and Solovay showed that these extensions preserve large cardinal axioms if these axioms hold for a proper class of cardinals. That's one reason why I was stating things that way. So if large cardinal axioms can help here, it can only help in some very indirect way. And one might have hoped that by bringing in infinity principles, one might actually resolve CH. But this result says, well, that's something strange and unexpected has to happen. Okay, so now we want to look more closely at this problem of CH. So there's logical definability. A formal property is any property which can be expressed with finitely many instances of there is a set for all sets. A is an element of B. A is not an element of B, and or. The property C equals D is formally by the axioms simply that property. Two sets are equal if they have the same elements. That's why I didn't need to put A equals B as one of my primitive notions. Okay, so that's all standard. If X is a set, we can restrict there exists a set, and for all sets, to just elements of X. And in doing so, we can interpret that property within X. And this is where things get interesting. So that's logical definability within a set. Suppose X is a set. A subset of that set Y is logically definable in X from parameters if there's a formal property, some parameters, A1 up to AN of X, such that Y is the set of all A in X, such that the property holds at A with the parameters A1 up to AN, but within X, where you restrict everything to X. Formal expressions are finite, obviously. However, X can be infinite and quite complex. Simple definitions in a complex setting can yield complex results. Every notion of mathematics can be realized as a formal property of sets, and those of number theory can be realized where X is V omega. Okay? So don't be deceived by the simplicity of the properties. Okay, so we have to deal with the ramifications of Cohen's method. We want to do that by refining the concept of our set, or can we? So Cohen's method of blueprints has been vastly developed in the 50 years since it was discovered. Many questions have been shown to be unsolvable. It's not just the continuum hypothesis. It's a serious challenge to the very conception of the universe of sets. And the continuum hypothesis is just a statement about V omega plus 2, which is way down at the bottom. So what sense does it to have a conception of large cardinals, which are way up high, if you can't even answer the basic questions about small sets? So in that sense, it's a serious challenge to the conception of V. Okay, so let's now try to refine the concept of set and see if that leads us anywhere. So we'll introduce the definable power set. For each set X, we'll let P def of X denote the set of all subsets of X such that which are logically definable in the structure X epsilon with parameters from X. So the power set of X is the collection of all subsets of X. P def of X is the collection of specifiable subsets of X. Somehow, it's those sets which you're generating from X itself. You're not going out into the nebulous beyond and collecting sets.
You mean Y is not specific?
Pardon?
Y is not
Y, where? Here?
specific.
Set of all Y such that Y, yes, that's a Y. Those two are not there. There's a little vertical line coming straight down. And yes. You know, you look at slides again and again, and you always see what you think you wrote, never what you wrote. All right, so they're the projective sets. These are not the projective sets in algebraic geometry. These are the projective sets from analysis. A set of reals is projective if it can be generated from the open sets in finitely many steps of taking complements and images by continuous functions f from R to R. So the open sets from the point of view of analysis are simple sets. In fact, they're just specified by the sets of rationals that lie in them. And the study of these sets was a major focus of the polar school of mathematics in the early 1900s. Now, the reals, in any reasonable presentation, are a subset of v omega plus 1. So the power set of the reals is a subset of the power set of v omega plus 1, which is v omega plus 2 by definition. The collection of the projective sets is just the power of the reals intersect the definable power set of v omega plus 1. So in some sense, in terms of the definable power set, the projective sets are a very natural collection of sets. They're not defined that way, but it's not hard to show that that's exactly what they are. Well, if we can't solve the continuum hypothesis, let's narrow down. So let's formulate the projective continuum hypothesis. If A is an infinite projective set, then either A and N have the same cardinality, or A and R have the same cardinality. There were many attempts in that polar school in the early 1900s to prove the projective continuum hypothesis with success for the simplest instances. However, by 1925, it too began to look like a hopeless problem. It was. The actual constructions of Cohen and Gödel show that the projective continuum hypothesis is also formally unsolvable. If you just literally take the universes that they constructed, this explains why the problem with the projective continuum hypothesis was so difficult. But the intuition that the problem has an answer was correct. Here's the theorem. Suppose there are infinitely many Woodin cardinals. Then the strong projective continuum hypothesis is true. The strong projective continuum hypothesis simply asserts that every uncountable projective set contains an uncountable closed set. It was known that the continuum hypothesis holds for the closed sets. And so if you have an uncountable projective set and it contains an uncountable closed set, that uncountable closed set has to have the same cardinality as the reals, and therefore it follows that the projective set that closed set was sitting inside must also have cardinality of the reals. So maybe the problem of the continuum hypothesis also has an answer, and maybe the key is the definable power set. All right, so let's bring that out. I'm not inverting history a bit, but let's bring that into it. Remember the accumulative hierarchy, that nice presentation of the universe of sets given by the transfinite iteration of the power set operation. Picks up all the sets. Well, let's replace the power set by the definable power set. And that's Gödel's constructible universe, which is denoted L. So it looks very similar. You start with nothing. At a successor step here, you take the definable power set, whereas at the successor step here, you take the full power set. Otherwise, you do exactly the same thing. You take unions at limits. L is the class of all sets such that X belongs to L alpha for some alpha. Now, L alpha in general is not V L intersect V alpha. So it is for some alphas, but it's not always true. The axiom V is equal to L is simply the axiom that if X is a set, then X belongs to L. So the axiom V is equal to L says you generate all sets by the transfinite iteration of the definable power set. And then Gödel proved, assume V equals L, then the continuum hypothesis holds. That's how he showed that the continuum hypothesis couldn't be refuted. suppose there's a Cohen blueprint for V is equal to L. Then the axiom V equals L must hold and the blueprint is trivial. Adopting the axiom V equals L completely negates the ramification of Cohen's method. Could this be it? Looking good. We have an axiom that settles the CH and an axiom that is immune to Cohen's method. Well, if it were, I would not be talking about everything else. So there is a problem. Before Cohen's work, a few years before, 2 years I guess, Scott showed the theorem that assume V is equal to L, then there are no measurable cardinals. In fact, in the modern language, there are no genuine large cardinals, where genuine is stated an ambiguous notion. In particular, if you assume V equals L, there are no Woodin cardinals, because Woodin cardinals are bigger than measurable cardinals. So, of course, the axiom V equals L is false. Now, there's an obvious response. Some might say this is a desperate retreat. That's the intermodal program. Let's construct enlargements of L in which large cardinals can be verified to exist. But let's do this by using the large cardinals to expand the definable power set. One could view Scott's theorem as saying the definable power set's too simple. We need a richer definable power set. So the question is, we have the definable power set and the full power set. Maybe there are interesting intermediate notions, and that's where we need to look. Okay, and then there's the glimmer of hope, the theorem of Mitchell, Steele, and company. Suppose there are infinitely many Woodin cardinals, then for every finite number n, there is an enlargement of L in which there are n many Woodin cardinals, and the strong projective continuum hypothesis is false. What does this show? First of all, it shows there are enlargements of L in which large cardinals can be verified to exist. So there is an enhancement of the definable power set that can lead to universes which can accommodate large cardinals, at least at the level of Woodin cardinals. It also shows something else, that proof that the strong projective continuum hypothesis from the existence of infinitely many Woodin cardinals was optimal. You couldn't do it with finitely many. So that's an interesting side. And the details show that even the projective continuum hypothesis cannot be proved from finitely many Woodin cardinals. So the cardinals have a lot of power, but the power is limited. Okay. Well, there's a skeptical assessment now. The program to understand V through enlargements of L can never succeed, because there can't be an ultimate enlargement of L since one cannot define an ultimate large cardinal axiom. Well, except for maybe 0 equals 1, but that's not so interesting. More precisely, there can be no ultimate enlargement of L since its construction would require having identified all higher notions of infinity. Because remember what the methodology is. We use the large cardinal to enhance the definable power set and then do the construction. Okay, well so with every enlargement, there's going to be a generalization of Scott's theorem. Because you didn't use the largest large cardinal to get the ultimate enhancement of the power set, so it's going to be limited. And that's exactly what's been happening. Do the Mitchell-Steele construction to get 1 Woodin cardinal, you don't get 2. Do it for 2, you don't get 3. Do it for 3, you don't get 4. So this seems like a pretty compelling skeptical assessment. Maybe it's time to give up. Well, large cardinal axioms are not provable by Gödel's second incompleteness theorem. But they are falsifiable. So here's my prediction I've made before. No contradiction in the existence of infinitely many Woodin cardinals will be discovered within the next 1,000 years, not by any means whatsoever. Now, you can be a finitist and reject infinite sets. But how do you explain such a prediction if it's correct? I mean, you either have to take the position, so that truth could be, we wait 1,000 years, but such truths that there is no falsification of an axiom, you can never prove that. So it suggests there's a component in the evolution of our understanding of mathematics which is not formal, which is not entirely based in proofs. The skeptical assessment must be wrong. How else can these predictions, if they're correct, be explained? No one has come up with a methodology for accounting for the consistency of large cardinals other than something that traces back to they're consistent because they exist in the universe of sets. And if they exist, they're not inconsistent. And that sounds like I'm being frivolous, but that's true. So there's something going on here. What is it? I mean, if you're going to say, all right, I'm going to have the universe of sets with these large cardinals, I can't answer the continuum hypothesis question, that feels a little strange. You're asserting something about big sets and giving up on the small sets. All right, so let's go back to our large cardinals again, the sampling. We had a proper class of measurable cardinals, strong cardinals, Woodin cardinals, super strong, then super compact, extendable, huge, and omega huge. Again, these are just mileposts in the current hierarchy. Something completely unexpected happens. The enlargement of L for exactly one supercompact cardinal, no more and no less, is provably the ultimate enlargement of L. The Scott phenomena ends. Now, I'm not stating the exact theorem, there are assumptions here, but the spirit of this seems very much true. Now, this explains why no progress was made at the level of supercompact cardinals and beyond in the intermodal program. Because no one's just going to go for one supercompact when you'd rather go for two. Or go for two when you'd rather go for three, or go for huge. Why would you only go for one? And the answer is you can only go for one. It's not because one supercompact cardinal is the ultimate large cardinal, though I suppose that could be the case in the end if everything stronger is inconsistent, but that's not what's going on here. Instead, it's because something completely new happens. And in the other talk I wrote, which was more technical, I would make you sit through a lot of reasons, but I'm not going to do that. I will say there's a very good candidate for the axiom V is ultimate L, even though we don't know how to construct the enlargement yet. So if you think back to the axiom V equals L, you can only state that axiom if you have the definition of the L alphas, the level by level construction of L. So you would think, even if there is an ultimate L, you're not going to be able to write down that axiom until you have the level by level construction. And that turns out to be possibly not true. The formulation of the candidate axiom involves an abstract generalization of the projective sets and another hierarchy defined by Gödel. All right, so now I realize it's a little frustrating. I haven't given definitions or certainly any proofs, so now we're going to get into the details. First, before we do that, if you assume this axiom, V is ultimate L, then the continuum hypothesis holds. Well, we would expect that. Suppose there's a Cohen blueprint for V is ultimate L, then the axiom V is ultimate L must hold and the blueprint is trivial. So these are theorems we can prove now from this formulation of the axiom. So the axiom V, we can also see that the axiom V is ultimate L settles modulo axioms of infinity, all sentences about small sets like V omega plus 2, which have been shown to be independent by Cohen's method. Adopting the axiom completely negates the ramifications of Cohen's method. And one's almost conceivably in the situation that Gödel had speculated all, where everything gets reduced to infinity principles. Okay, so those are, each of these is a precise theorem. Okay, now the fine print. I just want to show you that it's not some 20-page axiom. It's an axiom that can be defined in a first-year graduate course. And some of these notions I've already mentioned. There's strong cardinal, there's Woodin. This is a notion in the Levy hierarchy. And it just says that if a certain kind of sentence holds, then there's a universally bare set such that the sentence reflects to something. So the universally bare sets are an abstract generalization of the projective sets. I can tell you what they are. Sets universally bare if its continuous preimages in every topological space has the property of bare in that space, an elementary notion. Hod is that other hierarchy defined by Gödel. It's the class of hereditarily ordinal definable sets. So Gödel showed that inside any universe of sets, whether the axiom of choice holds or not, there's another way to build a canonical, but not truly canonical, ZFC model, and that's called Hod. So that's the other hierarchy. What's L of A and R? That's the iterated definable cumulative hierarchy, but built over A. You throw in A at the bottom, and then you do the transfinite iteration of the definable power set. Then in that class, which you compute Hod, and then you cut it down to an ordinal, and that's supposed to reflect the truth of phi. What's theta? Theta is a ZF measure of the size of the continuum. It's the supremum of the ordinals onto which you can map the reals. If ZFC holds, theta is the cardinal successor of 2 to the aleph naught. But in the ZF setting, you don't have a well-ordering of the reals, so things can get quite complicated. So this axiom brings together many current themes, this formulation, which are going on in this program. We have the universally bare sets, we have determinacy, and so forth. So that's the axiom. And I just wanted to show you that it's this axiom which you can write down. But having written that down, one can ask, is there a generalization of Scott's theorem to this axiom? Maybe this axiom implies there are no huge cardinals, or maybe it implies whatever. This axiom implies CH. This axiom implies that V cannot be obtained by a Cohen blueprint. So those all become, this is the axiom that made those theorems precise. For the set theorists in the audience, this axiom implies that V is not a generic extension. It implies that it's the minimum universe of the generic multiverse. But we still have this problem. All right, we have an axiom. However we might motivate it, how can we be sure that there isn't a Scott's theorem? And then we're right back to the problem with L. Well, so that brings us to the ultimate L conjecture. So suppose that delta is an extendable cardinal. Then necessarily there exists a transitive class N such that N is a weak extender model for delta supercompact. N satisfies the axiom V equals ultimate L, and N is sigma 2 definable from parameters. The last is not really so important. I just don't want to have to deal with quantifying over classes. If the ultimate L conjecture is true, that means provable, because necessarily, then it would show there's no generalization of Scott's theorem to V as ultimate L. There's a very precise theorem there. This is by what's called the universality theorem for weak extender models. There's a certain way that large cardinal axioms are posed, and you get it out of that. Okay, so it all comes down to this conjecture. If one can prove this conjecture, then one has an ultimate generalization of L and has very strong evidence that it's compatible with all large cardinal axioms, which is what I would say is the main deficiency of L. Gödel's axiom L is not compatible with large cardinals. All right, so what's the future? I would say the ultimate L conjecture is now the key problem. I think if the ultimate L conjecture is true, and that means provable, then there's an absolutely compelling case that V is ultimate L. People will disagree. But you have to come up with a reason. So we have the ultimate L project. So the program to prove the ultimate L conjectures naturally began as a 4-stage project. Stage 1's been completed over the last, about a year ago. And so arguably the ultimate L conjecture has survived its first critical test, because it could have been falsified there. That's why stage 1 was stage 1. In a surprising twist, the remaining 3 stages have recently collapsed into a single final stage. So that's kind of a good news, bad news. That could be a precursor to the ultimate L conjecture's false, or it could be a precursor of actually finding out the way to prove it. Too early to say. All right, but the ultimate L conjecture could be false. Now, hopefully we're not going to have to wait till the next century to learn the answer. All right, because I don't want to wait that long. All right, so I said, I'm going to finish a little early, the wine is waiting, that I was going to give you a treat. So I'll do it. So the components of large cardinals are called extenders. That's how we build these enrichments of the definable power set, and they're really sharps. So we're, you might say, analyzing distant sharps. Well, I have to show you a great picture of a very distant sharp on another world. And that's kind of what set theory is dealing with right now. Is there a world? So here is a picture from 3 days ago and NASA of Mount Sharp on Mars. Great picture. I'm not making the title up. That is Mount Sharp. So I see in closing that the subject is at a critical stage. The ultimate L conjecture could be true, and that will take set theory in one direction, or the ultimate L conjecture could be false, which would take the set theory in another direction. About the consistency claim, some people have stated that large cardinal axioms are consistent because it's in the nature of how we formulate them, that if they're inconsistent, they fall apart quickly. It's in this, it's just something about the nature that there's never going to be, and there hasn't been to date, a simple refutation in the end of a large cardinal axiom. Doesn't mean that the first refutation, large cardinal axioms have been proposed that have been shown to be false. And sometimes the first proofs are very complicated, but then it distills down and becomes simple. If the ultimate L conjecture is true, there'll be a whole new generation of inconsistency proofs, of axioms not now known to be inconsistent. And if they go by the route of proving the ultimate L conjecture, they are not elementary proofs. So there's the real possibility that in this landscape of consistent versus inconsistent, there may be no simple way of doing the triage into, oh, that's clearly consistent, that's clearly inconsistent. There may be very subtle reasons that define how the large cardinal hierarchy defines and separates those consistent axioms from the inconsistent. And if that is true, then that just reinforces everything. It makes it all the more unlikely that you're going to have a methodology or a conception that explains the consistency statements. Remember, those are the falsifiable statements from large cardinals that doesn't trace back to set theory and the existence of those large cardinals. And so that's really the key question. If these consistency statements are true, why? And is it any evidence that the conception of set theory is meaningful? And again, you know, people have tried, and the people who have taken these consistency statements and reworked them into plausible statements about small sets that look completely different. But that does not justify the consistency. For example, the Riemann hypothesis is a pi-0-1 sentence. Suppose you show that the Riemann hypothesis is equivalent to the consistency of a supercompact cardinal. Is the Riemann hypothesis true? So there's something special about the large cardinal axioms where they are falsifiable statements that we feel somehow we can make the case that they are true. And it's not just because they're strong. You know, if you prove the Riemann hypothesis implied con ZFC, is that evidence that it's true? Well, no. There's something different about the large cardinal hierarchy. And so the question is, what is that? I would say it's because of the universe of sets. But maybe there's another reason. And so that, I think, is the real question that I invite you all to think about. Why is it that we can make these claims and believe that they might actually be true? Now, of course, I'll look pretty foolish in 1,000 years, well, in here, if someone were to refute the consistency of ZFC. Well, then it's back to the drawing board. But you know, that is the question. Large cardinals, I mean, in some sense, set theory is the purest of the pure and is so far from applied that there's no pretense that, you know, it's going to help with national security or whatever. But it does make these predictions about small sets. And there's no other way to make those predictions. And so one needs to understand why. Anyway, thank you for your time and thank you for coming.
John is still here. John, do you want it? Okay. John asked me to handle the questions. Questions? Yes.
So does it mean that if you prove this ultimate L conjecture, then because there is no sharps for ultimate L, does it mean that these cardinals which are bigger than supercompact are inconsistent or something like that?
No, it's in part true. There's a concept that ultimate L construction will be a model for which there's no sharp. But that model is very close to V. And so V doesn't have a sharp. So it's a construction within V that's close enough to V that it inherits the non-existence of sharp from the non-existence of the sharp in V. The surprising and unexpected thing is that you can conceive of building that construction focusing only on supercompact. And that's because even though you will build this model using only the one supercompact in the parent universe, all the other large cardinals flow into the model. That's the new phenomenon. It's not that supercompact is stronger than everything. It's that the constructed L-like model for supercompact, for magical reasons, just picks up everything from V. It's like a great attractor. And it brings in all the large cardinals that exists in V.
What do you mean by it's close to V? You can force V? Or?
Well, so in inner model theory or in set theory, we have various metrics that say that an inner model, a sub-universe of V, is close to V. One metric is that it computes successor cardinals correctly for many cardinals. And this ultimate L will provably do that. So it will produce, above the supercompact where you've constructed it, it will compute the successors of all singular cardinals correctly. So that's a standard metric of closeness. Okay, so from that, you would expect universality from the experience in inner model theory. The remarkable thing is that you can prove universality from that. And so predictions that were made from the inner model program have gotten verified in a very abstract setting. So again, I want to emphasize the ultimate L, even though it will be built for one supercompact, it can have far more in it. That's that surprise, that unexpected surprise, that there's a way of enriching the definable power set relative to supercompact that gets you the richest enrichment that you can imagine for reasons that are a surprise.
This picture from Mars could be from Arizona.
Good. It's a wonderful landscape because there are no plants.
Okay. So, so there are these two worlds, Earth and Mars, which sort of look a little bit similar, but then there are some differences. So what do you have to say to people who think that maybe mathematics beyond infinite is such that there are maybe 2 or 3 worlds? They look by and large similar for definable sets and so forth, but then when you look very carefully, the telescope or microscope, then there are actually some differences, like maybe CH. What do you say?
I mean, CH is a great problem. 15 years ago, if I were giving this lecture, I would have been telling you why CH was false. All right? Well, times change. I think that a conception of a collection of universes, maybe it's 2, 5, or whatever, I think one has to somehow, how is one going to package that into a convincing a philosophy of truth? That would be my only question. I mean, there are, in my mind, 2 subjects in set theory. There is the subject of trying to understand what V is, by whatever means we can. Then there's another subject, and that is the mathematics of models of set theory. What can be true in a model of set theory? I don't see why these have to be the same subject. They're certainly not in arithmetic. Study non-standard models of arithmetic doesn't mean that you're undermining the conception of true arithmetic. You might want to study models of arithmetic in which arithmetic is inconsistent. There are formulations of P versus NP that deal on trying to understand that very problem. Does that means that you need to have somehow accommodate all of these? So my response is, I see at this point, I don't see a coherent basis for a conception of anything other than a single V if the ultimate L conjecture is true. It's going to give you, in this universe of sets, assuming only a modest large cardinal hypothesis, an inner model of V that just cries out to you. It's very close to V. It accommodates all large cardinal axioms. And I just don't see, if you're going to reject that as V, one has to have a reason. And I don't think the reason, well, I have this very good theory over here that's good for analyzing these structures. I don't see that as a basis yet. It would be a little bit like, there's a huge subject in set theory of determinacy. And it gives a very rich structure theory. Now, you can view it 2 different ways. You can view it as, I'm going to live in that world where determinacy holds and analyze my objects. Or you can study the objects that we see that belong to those inner models, the simple subsets of reals, the simple Banach algebras, whatever. And so you can view the successes of that as a kind of a definability theory. It's saying that certain kinds of objects, if they're simple enough, have a rich structure. The forcing axiom successes can be packaged this way. If you assume CH and you have AD and L of R, they're Pmax extensions of L of R. So there are well orderings of the reals that live in these very simple universes, and you can analyze those structures. You just have a richer family of things that you can analyze, and they can accommodate well orderings of the reals. So I don't see a tension why one has to say, I want 5 universes, or 6, or 7, or 13, or whatever, and you just decide which one you're going to be in. I mean, that's all. I mean, I don't see how one makes the case for that.
Since you yourself mentioned your former self 15 years ago, maybe you can say something more about this. If I recall correctly, there was a theorem that said that if you have certain demands on theories, then any theory that meets these requirements will have to prove the negation of CH.
Okay, so that
And how does this...
Okay, so that theorem rests on a couple of conjectures which are open. One of the conjectures, one component, was the omega conjecture. In this emerging scenario of the ultimate L conjecture, the status of the omega conjecture is not at all clear. I mean, one can make the case for that. I mean, there is this very canonical axiom for not CH that feels like a real closed field extension. It's maximizing a two-quantifier theory. And about 5 years ago, it was shown that if you condition that on CH, it can't work. So there is a very attractive argument that if you want to maximize a for all there exists, it's like roots kind of theory, there is a kind of canonical and unique way to do it, and if you try to condition it on CH, it doesn't work. And so one could try to build up a case for not CH that way, and that's what I was trying to do. But to me, this is kind of like an R-centric view of the universe. The universe of sets is a really big place. Why should these very small sets dictate what's going on? And that's kind of what one is saying, that an attractive theory for P of R, or P omega 1, will tell you that that's true, independent of whether that integrates with a comprehensive and global theory of V. And that's where it fell down. There didn't seem to be any way of merging the attractive theory at the level of omega 1, or the reals, into a comprehensive global theory of V. And so I was dragged in some sense kicking and screaming from that picture. I thought that was a great idea, this canonical model of not CH. But it didn't fit. And sometimes you have to go where the investigation leads you. Why can't we have a conception of V, an axiomatic conception of the universe of sets, that is as robust as our axiomatic conception of the integers? That's the real question.
No.
Well, so you said that the ultimate L conjecture, if true, will give us many new insights, and I think we are all convinced. You also said that if it isn't true, it will give us many new insights. And
I'm
of
sorry?
course, you have said also that if it is not true, it will give us new insights. That is more difficult to understand.
Yeah.
Perhaps if there is no model for a super compact cardinal L-like model,
Yeah, there
that
could be,
might.
yeah.
So if you could just explain that.
Yeah, well, I'll say two things. First of all, if the ultimate L, the evidence for the ultimate L conjecture could be the precursor to there is no ultimate L because the intermodel program fails at supercompact. It's too good to be true. If the ultimate L conjecture is true and provable, then one has a serious foundational issue. And that's this. Up to now, or up to supercompact, I would take the view, and I think others would as well, that the successful construction of the enlargement of L gave us our deepest insight into that large cardinal axiom, and in some sense certified its consistency. Because if it were inconsistent, how could the construction have worked? But wait a minute. You build ultimate L using only supercompact. So it can't possibly provide the basis for the consistency of large cardinals beyond supercompact, even though they're present. You didn't put them there. They got there by magic. So there'll be a serious foundational challenge. How does one in the ultimate L environment justify convincingly the large cardinal hierarchy beyond supercompact? And if that's going to be a serious challenge. Now there are scenarios, and the scenario is, and there are already precursors of this, in the ultimate L environment, maybe there are patterns visible that are otherwise invisible. relationships between, in other words, I mean, I don't want to get technical, but there could be equivalences to large cardinals. Different formulations are equivalent in the context of V is ultimate L that aren't otherwise equivalent. For example, consider the statement AD holds in L of R versus the axiom of choice fails in L of R. Those are not equivalent. But in the L context, in the intermodal theoretic context, I think that's proved equivalent. Yeah, they're equivalent. That's the theorem of Steele. So in the context of I am an enlargement of L, we see that AD/L of R is simply equivalent to the axiom of choice, fails in L of R. That's an equivalence invisible in ZFC. And there are scenarios for generalizations of that at higher cardinals. And so in this confine of ultimate L, you might see relationships to verify. It's going to be, if large cardinals are going to be certified as consistent beyond supercompact, it's going to be because they represent complexity of ultimate L. And how that plays out will be the key. Okay? So that will be the challenge. If that doesn't happen, I think there's a serious problem.
So Hugh already mentioned the wine, and the wine is still waiting. Everyone is cordially invited to the wine reception outside, and let us thank the speaker once more.